This is Taibiao, and my presentation is about a paper from Mohammed Jamal in the last year. And the title of this paper is Rethinking Class Balance Method for Long-Tailed Vision Recognition from a Domain Adaptation Perspective. So it's a paper about the long-tailed recognition, imbalanced recognition. So there are 4 sections in my presentation: introduction, theoretical analysis, and experiments, and the last is conclusion. So for the long-tailed problem, you maybe ask what it is and when it happens. So object frequency in the real world often exhibits a long-tailed distribution, as this figure shows, where a small number of classes dominate, like the common and uncommon objects in context, and positive patients and negative patients in medical diagnosis. As you know, the uncommon objects in context are dominant, but the size of them is very small, and the positive patients are dominant, and the number of them is small. So when is this problem happens? So the long-tail problem emerges as the datasets grow in scale, and it is prevalent in fine-grained recognition detection. The structure of these datasets, like this curve, and the head classes and the tail classes. So you can see them from this curve. The number of the head classes is very large, and the number of the sample in the tail classes is very few. So in these recognition techniques, present challenge for this classification task, especially for the tail classes, because there lack of the examples, lack of data. So here is this problem statement. The training set is a long-tailed distribution. It means you train the model on the imbalanced dataset. Now you can see from these the head and the tail. But the test set, we all know this balanced distribution. And for the existing method in this problem, there are 2 categories: rebalancing the data and rebalancing the loss. In the rebalancing data, there are many techniques like upsampling the tail classes or downsampling the head classes. But both of them are not good enough. As you know, if you upsampling the tail classes, the model may be overfit. If you downsampling the head classes, it will lose some features.
Taibiao, I have a question here. So
okay.
Here, so your training set is unbalanced. Why the test set is balanced? So what's the real world scenario? I think so in the real world, so in most cases, both the training set, it can be like balanced, is unbalanced, and the test set is also unbalanced. So I'm confused why here the test set is balanced.
Oh, okay. Because like the example I said before, the patients or the uncommon and common context, you may train a model by this imbalanced dataset because the dataset is big, it's very large, and the abnormal classes is very small. So you use this model to predict some like images. Maybe there is just one images, I think.
Yeah, but in this case, it doesn't matter whether the test set is balanced or unbalanced.
Oh yeah, yes, because they use this test set to evaluate the model, the trend in this
But when you
imbalanced
perform
data.
the validation, So you just like the image you will input one by one. So I cannot figure out why here. So so set this as the balance. It's like the artificial problem. So so actually it's not necessary to have this requirement, right?
Uh, mm, yeah, but I think the test data, if the test data is imbalanced, it doesn't make sense because the distribution is the same and the model you don't need to the model imbalanced or balanced. That doesn't matter.
No, I think the test set is imbalance is that no matter, and also it makes sense. So because so here the problem I'm to solve the imbalance reward problem. So why the training set is imbalanced is because so in some case for some some sample is very hard to label, and but for the common data, common sample is easy to label. So that's why the training set is imbalanced. And for the
Yeah,
test
yeah,
set, yeah, it's the same. For the real world data, you have when you perform the testing. I think so. Also for some case, it belong to the minority. So it's also
yeah,
imbalanced. But
yeah,
here
yeah.
the
Yeah.
yeah, here the balance or imbalance for the test set, I think it doesn't matter. So that's why I'm confused why. So here they need to have this requirement for the test set to be balanced. I don't think it will impact the problem because for the data they will input one by one.
Yeah, yeah, I know. But when you evaluate your model by the test set, it'll be if you use the imbalanced or balanced, the result will be different. And for your question, I think because in this imbalanced data set, I think the tail classes are more dominant. So they use this model training in the imbalanced data set to get a very good model can classify the tail classes and the head classes. If the test set is imbalanced, um, the accuracy of the model evaluation maybe um, cannot cannot express how the important the tail classes is.
Yeah, I agree. Because I think for the balanced testing data set, it's like for fairness, right? We should respect every class rather than lower the priority of those classes in the long tail. So if we have an imbalanced distribution, like have a similar distribution like the training set, then the model eventually trained will have less accuracy over the class in the long tail. But because the testing set is for testing, right? We wanted to evaluate the quality of the model and to be fair to all the classes. Then that's why I think we should have balanced the testing data set.
But it's not necessary. So when you test your performance of your model, you just like consider like all for performance and metric like the precision, accuracy, and the recall. So if like and F1 score, if all of them are good, that means it can can better to recognize this minority sample. That should be good enough. And if you claim that here have this setting, just want to test the performance of model, I think it doesn't make sense other way. And also in the real world data, so typically the training set and test set they should have the same distribution.
But I would to say, I mean, the long tail data distribution in the training data set might not be able to represent the real world, because some of the data in the long tail is because it's rare. Okay, it's hard to collect. That's why the amount of the data is small. It's not. It doesn't mean. I mean, in the real world, we only have a small amount of data like this. Right.
Actually, I don't agree with this because I work in for this practical dataset things. So most of datasets, so that belong to this minority classification problem, have this long tail problem. So you can see that for most of the datasets, just like the just what we have done for this malicious content classification. So the common contents always dominate the network contents, and for the like malicious content, it's only like occupies a small portion. And also for other cases, like if we consider like so the medical image, so you can see you can also, it's easy to understand that the common image dominates the all the data, and for this uncommon, for some disease, it only occupies a small portion.
But I think in the I think this paper, they think the tail classes is more valuable than the head classes.
Yeah, that's true. That's true. I'm also
So if the test set is imbalanced, it means there are some tail classes. The number of the tail classes is very small. If the prediction is wrong, it doesn't matter. The accuracy will as high as.
Yeah, that's why I said you cannot use the accuracy. I think the recall is the most important. Yeah, you need to guarantee that the accuracy, precision, and the recall, and also F1 score, all of them are good. Typically, the recall is most important. If you can have the high recall, so you can, that means you classify this minority, so with a high accuracy. So definitely, if you just use the accuracy, just like all the minority are classified into the majority, you can still have like 99 something the performance.
Yeah, that makes a lot of sense. Yeah.
Anyway, this doesn't matter, so you can go ahead.
Okay. Okay. So
yeah, we can revisit this at the end of the seminar. I mean the presentation. You can
think about this.
Well, it's like an extreme case.
Yeah, you can think about this after presentation. So why they use this balanced distribution? It's looking, so to me it looks weird. So it's not necessary, but probably it's just my thinking. Yeah, you can go ahead.
Yeah, I will talk about this balanced distribution later. I think because of the algorithm in this paper, the test set must be the balanced distribution.
Okay.
So we will talk about it later. So for the long-tailed recognition, and the existing method are rebalanced data and the rebalancing loss. We have talked about the rebalanced data before, and in rebalancing the loss, it assigns large weight to tail classes and small weight to head classes, like the class balance formulas and LDAM. So in this figure, you can see in the classification line, the black line is no reweighting line, and here is the tail classes and here is the head classes, and the red line is reweighted result. I think the red line is more reasonable because, as I said, the tail classes is more valuable in this paper. So for current method, these methods overfit the head classes and fail in the tail classes, and they implicitly assume that the test distribution is the same as the long-tailed training set. So here is the result of current method with course entropy and the learning to rewrite loss function. And neither of them work well on the test set. And you can see here is the result. Here, the accuracy on the tail class of the course entropy is very low, and the accuracy of the head classes of the learning to rewrite is not good enough. They're only 0.68. So as a result, this paper is going to training a model to uncover these assumptions that the training set has the same distribution with the test set. There are many long-tailed datasets like eNeutralist and LVIS and ImageNet and Cuckoo, etc. And you can feel the distribution from this image. Yeah, the head classes, and they have majority samples in the whole datasets. So here is the theoretical analysis. This paper, they represent a novel perspective, domain adaptation. And the source domain is the training set, and the target domain is the test set. But these two distributions are different. And so the object of this paper is learning a model on the source domain and make it work well on the target domain, the test set. For previous works, they provide the assumption about the target shift, that the distribution like this, the data on common slider is the head classes is equal to the x is equal to the data common slider. This is a distribution on the target domain, and here is the king eater class. They provide these assumptions, but it is reasonable because this assumption can make a good algorithm for this long tail recognition. Yeah, but it is wrong since this king eater is a tail classes. The lack of examples for completely represent the features of the tail classes. But you can think the first equation maybe is right, because the common slider is a head classes. There are abandoned images, abandoned examples in these head classes, so they can represent these classes completely. So in this paper, they're going to accounting for this equation, the distribution data on king eater from the source domain is different from the data king eater distribution on the target domain. And here is the equations. This is the error, the loss function. The F is the recognition model parameterized by the theta, and the L is the loss function. So through the first two lines equations, you may see there. Here is the PT, is the distribution on the target domain, and here is the PS. This is the distribution on the source domain. So through these two line equations, it makes the domain transition. So here is the W and epsilon. There are two parameters. In this paper, we will talk about them later in the algorithm. So the loss become in these equations. Here, the L is an unbiased loss function. You can use any loss function like as the L, like a cross entropy, like a focal loss, and the NA loss function. And here is the W and epsilon. They are the two components, and it is the point in this paper. In the next section, we will talk about how to learn these two components. First, for the class-wise weights W. Supposing there are ny training examples for the Y's class, then it gives the Y expressions. The beta is another parameter, we don't think about it. The n is the number of the training examples. So if you stared at these equations, you can find it only depends on the number of samples in the classes. So I give an example, like in the CFAR10 long tail, the WY, the first element is 0.29 and the last element is 2.3. It makes sense because the first element, this is the class-wide weight of the head classes. Because the head class has very large examples, the weight is relatively very small. And the last is the largest because the tail classes only has very few examples. Okay, next, we're gonna talk about the epsilon. In this paper, the epsilon is a condition weight. They use a program called meta learning to learn these weights. Let's take epsilon. Let's take the epsilon by solving the following problems. These two equations by minimizing the error estimation to get the theta and use this theta to perform best on the development set D. The development set D is a balanced data extracted from the training set. Yeah, the D is the balanced development data set from the training set. But it is not. It is computationally prohibitive to train for each set of weights to find out the best epsilon by these two equations. We can do it through it. So in this paper, the author they provide a modified meta learning framework to get the epsilon. Here, there are three backward propagation. For the first equation tries a one-step gradient descent for the theta t, and using the loss weighted by the epsilon t plus the wy. And the next, the model parameter epsilon t plus 1 hat then are used on the balanced development set D, which updates the conditional weight by one-step gradient descent. And now we get the epsilon t plus 1. And then they use the epsilon t plus 1 with the class-wide weights to get another gradient descent for updating the theta t plus 1. Then they will do this three propagation again and again to get the best epsilon. So here is the differences between this method in this paper and the learning to reweight. The learning to rewet is another method in this field in the long-tailed problem. They also use the class-wise wet and the conditional wet, epsilon. But here is the difference between these two methods. This method in this paper needs pre-training, but the learning to rewet doesn't. And the learning to rewet needs clip negative wet. This method doesn't do it. And the learning to rewet normalize the epsilon. And this method doesn't. So as a result, after the normalization and clip the negative epsilon, the free space of epsilon in the learning to rewet is reduced. But this method, the free space of epsilon in this method is full of real space. So from this point, this method is better than the L2 learning to rewet, because if the optimal epsilon is outside the reduced space, for the learning to rewet, they will never get the best epsilon. So here is the algorithm for the long-tailed recognition presented in this paper. Here are two stages about to learn the epsilon and the W. The first five lines, it doesn't matter, it's just a common training to. I think these 5 lines is just the pre-training for the model parameter theta. And then in the second stage, they train to get the epsilon and combine with the class-wise wet to get the best model. And you can see from these 2 blue lines, yeah, they use the balanced development set D under set D to get the best epsilon, updated epsilon, and then use the updated epsilon and combine with the W to get the theta under training set T. So it makes sense. And from this line and the 13 lines, you can find that do the initialization for the epsilon. Yeah, they set the epsilon at 0 from the start point a very single batch. So it makes sure that the epsilon is very small part of wet, because wet consists of 2 components, the Wy and the epsilon. Wy, as we listed before for the CFA 10, they're about 0.5, but the epsilon is very small. Here is the epsilon learned from the CFA 10. The left figure is from the imbalance factor as 100, and right is from the imbalance factor at 10. And you can see from this magnitude, the mean instance wet epsilon is very small. For the imbalance factor, it is a parameter. For example, if the imbalance factor is 100, it means the head class maybe contain 1,000 examples, and the tail class just contain 10 examples. So the imbalance factor is 100. I think this parameter define the distribution of the CFA 10 long tail or CFA 100 long tail. Now we talk about the experiments. In this paper, they use 6 data sets: the CFA and the iNeutralist and ImagineNet and Places. The CFA long tail 10 and 100, they constructed from the CFA 10 and contains 10 or 100 categories, about 50,000 to 11,000 images. and they extracted 10 images per class at the development setting, and you can see the distributions of the CIFAR long tail. The imbalance factor is here. They influence the distribution of the datasets, as you can see. And here is the I-neutral list and the pass long tail. They're all long tail distribution. And then let's talk about the loss functions used in this paper. They use the coarse entropy and the focal loss and this label distribution via margin loss. These three loss functions. And also there is another technique called class balanced loss. They use this W is the same as we described before. The W is class-wise weight. Yeah, so the class balance loss can combine with these three loss functions, such as the class balance, the coarse entropy, class balance, the focal loss. Here is the implementation details. The neural network is ResNet and the learning rate. They use an initial learning rate of 0.1 and then also decay the learning rate at 116th and 118th apples by 0.01. The batch size 100, and then train all models on a single GPU using the stochastic gradient descent use momentum. And the momentum, I think it is the techniques as moving average. Here is the result of CIFAR long tail 10. These values in the tables is not the accuracy, is the error. So as you can see, as we discussed before, the imbalanced factor is the number of samples from largest class divided by the number of samples from the smallest class. And this parameter also influences the distribution. Yeah. And there is another point I think that is notable. Here you can find the advantages of their loss functions become more significant as the imbalance factor increase. As you can see, this imbalance factor is 200, and for these two values, this 32 and this 29, the difference between them are 3, and for the imbalance factor as 10. Here is 12, here is 11. The difference is only 1. So the imbalance factor influence many results. At the same, here is the CIFAR long tail 100 classification error in this table. And maybe you can see the value in this table is larger than before because the dataset is more complex. It contains 100 classes in this dataset. There is also this method in this paper works well on the I-neutral list 2017 and 2018, and also works well on the ImageNet and places. For the details about these two datasets is different than before. Here is the learning rate and the neural network. Yeah, compared with the coarse entropy model, the learning to rewrite maybe improve the accuracy on the tail classes, but it sacrifices the accuracy for the head classes. We said before, the accuracy is only 0.68. But this method in this paper is very good. They maintain the accuracy on the head classes as 0.95 And also, they enhance the accuracy on the tail classes as 0.42, and before is 0.26. So this method is very good for the long-tail recognition. Okay, here is the conclusion. There are two major contributions to the long-tailed visual recognition. The first one is the domain adaptation perspective for analyzing the mismatch problem in long-tailed classification. And the second contribution is to relax this assumption to implicitly model the ratio between two classes condition the distributions. So that's all. Thank you.
Oh, okay. So yeah, Taibiao just did his presentation. So if you have any question, you can ask for now.